Okay, isomers take 2. As you'll notice, I have everything already written out because I've already done this. Luckily, I didn't dump the sheets before I dumped the video. I don't know what happened to it. The next group that we need to name are the stereoisomers, cis and trans. But before we get to that, I'd like to actually talk about different types of isomers. So first of all, iso, the Latin prefix means the same. So anytime you see iso, there's something similar between the compounds. There are 2 types of isomers. There's constitutional, and constitutional is how they are actually put together, how they are made. So the way that I kind of always remember it is the Constitution is what makes up the country. So if it's a constitutional isomer, it's the way that it's made that is different, even though the compounds have the same chemical formulas. And then the stereoisomer, which we're going to talk more about, is a conformational. It's made exactly the same way, but its orientation in 3 dimensions is different. Unfortunately, I didn't think ahead enough to bring a molecule kit home. I had no idea that we were going to be out this long, and I didn't bring it. So I might try to see if I can find videos where somebody else has videoed themselves with those organic molecule sets. So there are a couple different types of constitutional isomers. And see, I've made them. I'm going to fix this. I'm going to put one in here, positional isomer, isomerism. So there's these 3 that we're going to talk about first. The first is the chain group isomer. This one's pretty easy to understand. If I give you 7 hydrogens in a row, that is sometimes also called N-heptane, N meaning normal and normal meaning not branched. So this would be an example of an N. This would not be an N because you've got this methyl group coming off of it. You can just say heptane would be fine, but you will see some textbooks saying N-heptane. And I went to figure out what the formula for this is. I'd say, oh, C7H16. I could also draw a compound that was an alkane, so no double bonds, no other functional groups on it, that was also the same formula, C7H16, but I could draw it like this. I could draw 3-methylhexane. So what I've done to find a chain group isomer is I've taken off one of the methyl groups. Remember, if I take off one of the methyl groups and I stick it here, that's still the exact same 7-chain carbon. So that's no different. So what I would do is I would take off a methyl group and I would stick it on the now 2 position. And I would say, oh, is that a different compound? Yeah, it is. If I stick it on the 2 position, I guess in my previous example, I stuck it on the 3 position, that would be an isomer. I could also stick it on the 2 positions. So the chain group isomerism is just a lot of practice in being systematic. Take 1 carbon group off, a methyl group off, move it, not on the first one, because that would just be the same as what you had, right? On the 2nd, the 3rd, the 4th, the 5th, making sure that you cross out any duplicates if you'd been counting this way. Take 2 carbon groups off. Together, move them down the chain, and then put 1 in the first position and move it down, the remaining one down the chain, move, right? And then occasionally when you get really long carbons, you can actually take an ethyl group off, and you could go through all of those different combinations. Okay, let's quickly draw all the chain group isomers of C7H16. Straight chain 7. Now I'm going to look at a parent chain of 6 because I've taken off 1 methyl group. I stick it in the 2nd position. I stick it in the 3rd position. If I put it in the 4th position, that would be the same as putting it in the 3rd position. So that's it. There's just 2 of those. Okay, if I keep going, I'm just repeating ones that I've already done. Now I take 2 methyl groups off. First I'm going to move them together. So I put 2-2, 3-3, and 4-4 would be the same as 2-2. So I'm done with moving 2 together. Now I'm going to take 2 off and I'm going to move them singly. I'm going to put a methyl group on the 2, and I'm going to move the other methyl group to the 3 position and the 4 position. Okay, so that's about all that I can do there. Then what I'm going to do is, instead of taking 1 and leaving it at the 2 position, I'm going to take 1 and leave it at the 3 position. I've already doubled up. This I've already done. If I put something here, I'll see right away that that is exactly the same as this. So I'm technically done with this. I've looked at taking off a methyl group. I've looked at taking 2 methyl groups. The last potential is to take off an ethyl group. So take off 2, but instead of having it as 2 methyl groups, I could have it as an ethyl group. So 1, 2, 3, 4, 5. Is this an isomer? Right? And the answer to that's a trick question. The answer to that is no, it's not, because now your longest chain is 1, 2, 3, 4, 5, 6 with something coming off the third. That is just this. So that one doesn't count. You're gonna be careful for that ethyl. Remember, you can't have a methyl in a 1 position. You also can't have an ethyl in a 2 position. So now let's try the ethyl group 2 in. If I do this, let's take a look at what our longest group is. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. This is actually an isomer because you actually have an ethyl group coming off of a 5 chain, right? So that one does work. That's a valid isomer. And if I move my ethyl group over here, it's just the same as that example. So that is a potential. Really, really hard to get a propyl group. Let's see if we can try. If I got a propyl group, I would actually only have a bute. So there'd be my 1, 2, 3, 4, and then my prop would be my, oh, Tony, get off. My propyl group would be 3, so 1, 2, 3, right? And right away you can see 1, 2, 3, 4, 5. I've already covered that. 1, 2, 3, 4, 5, 6. I've already covered that. So there is no propyl group. So for C7H16, there are 1, 2, 3, 4, 5, 6, 7, 8 isomers. It's a nasty test question because the test question would usually be, draw all the chain group isomers of C7H16 giving appropriate IUPAC names. Okay, so not hard to do if you're systematic about it. And again, just following those rules. Take 1 carbon off, move it all the way down the chain, get rid of doubles. Take 2 methyl groups off, move them together down the chain, then move them separately down the chain. If you have a sufficiently large enough compound, you could try taking an ethyl group and moving it down the chain. And if you have a really large compound, because you need something very big to actually have the propyl group, but that I've never actually seen a test question that looks at that. Okay, so that's the first on chain group isomerism. Now I'm going to look at more types of constitutional isomers. We're going to look at position isomers, and I'm going to go through this fairly quickly. A positional isomer is when you take a functional group, you don't change the chain group, the parent chain, you just move the functional group down the line. So this would be an example of 1 pentanol, or for you folks, pentan 1-ol. I could just move that OH group to the 2nd position. I could move that OH to the 3rd position. So that's actual positional isomer. Fairly straightforward if you don't have to fool around with changing the parent group and the functional group. I seem to be misplacing my markers left, right, and center. This could be a nasty question if I said, you give me all the isomers of this, because not only would you have to move the OHs everywhere, then you would have to move the OHs everywhere and the methyl group. So for example, you could have something like this. Your OH group on the 1st and a methyl group here, then move the OH there. That wouldn't count. Then you could redraw them all with the methyl group here, put the OH here, the OH here, the OH there, and the OH there. So you can see it's really, really nasty, but just, and very rarely do they ask questions because there's just so many different combinations. But that is just another type of constitutional isomer. They're put together differently. It's the same chemical formula, but the OH is on the 1st carbon, whereas here it's on the 2nd carbon. So it's just kind of more of the same, so I don't want to spend a whole lot of time on that. The other one that I'm not going to spend a whole lot of time on is functional group isomers. We haven't even talked about carboxylic acids or esters yet, but let me just put a little division here. When we get there, I will talk about the fact that they're isomers, and then you will remember this lesson. If you take a look at this, this is the carboxylic acid. I mean, technically we should call it an alkanoic acid, but it's one of those things that sticks around as a carboxylic acid. If you look for the formula of this, this is C2H4O2, so C2H4O2. This is an ester, which we'll talk about in another video, which I'm hoping to tape soon. It's C2H4O2. So they have the exact same chemical formula, but they're obviously connected very, very differently. So I'm not a big fan of making you memorize things, but if you're going to go on in organic chemistry, they talk a lot about this when they look at different types of spectroscopy. This is interesting because often when we get to the acid-base unit, I will always write this ethanoic acid or acetic acid as CH3COOH. And a lot of times people are like, why wouldn't you just write it like this? Because we normally combine the C's, the H's, and the O's at different times, but in organic chemistry, this tells me what to expect. I have learned that when I see COOH, really what that means is the C is double bonded to an O, and then it's also bonded to an OH functional group. If I saw that written like that, I would have no idea whether you were talking about the ester compound or the carboxylic acid. And it's really difficult to figure out how to answer the question if you don't know whether you're starting with this or if you're starting with that. So often I'll write it CH3COOH, and I can't stand textbooks that write it like that because I'm like, well, which one are you talking about? So the two common functional group isomers, which would be worth noting, are carboxylic acids and esters, and then the other one is an alcohol and an ether. The alcohol has that OH group on top. The ether just has the O stuck in the middle of the compound. So they also have the exact same chemical formula, but very, very different connectivity. And because of the polarity of the molecules, they have very, very different physical properties. And we'll talk more about that when we ever get to structures and properties. So I didn't want to spend a whole lot of time on them, but just to let you know that there's the three main ones: fool around with the chain, fool around with the functional group, moving along the chain, and then actually look at different functional groups for isomerism.